19.3, day number 1. You're sad. This is your third to last lesson of the year. I know, you are. You are. I'll keep posting more videos throughout the summer so you don't forget about school. It's important. Every day you'll remember. And you know what? I might even do a countdown. Every day I'll put a countdown of how many days are left until school starts again, September 4th. No, don't unsubscribe. Subscribe more. Okay, we're going to review. I called this the dot product. Dot product. It's also called the scalar product. We're going to find some perpendicular vectors, and then, you know what? Aren't vectors just lines? Yeah, I'm going to show you how to write vectors from vector form into equation of a line form. That's all it is. Cool. Okay, and then your assignment will be day 5. Let's jump into this. There's a creepy robot and some weird puzzles. This is the problem I would love to get into here. Go away, email. What would vector A be doing? What point would it be coming out of? Not that point. That's not a point. That's a vector. Where would it be established? Where does it start? At the origin, correct. And then it goes what direction? 4 units. Left 4 and down 2. Oh, show. So here's vector A. Okay, vector B. Where's that going? Right, 3, also down 2. Be really nice if those are symmetrical, but they're not. Could you find the magnitude of vector A for me? Let's talk through it. Magnitude of vector A in 2 dimensions is just the Pythagorean theorem. Follow? Okay, it's just the length of that vector. All I did was draw a triangle. Draw a triangle. Right? Pythagorean theorem would say that that length is root 20. How about vector B? Well, same deal. Now I'm just squaring 3 and 2. So I got 9 and a 4. Looks like root 13. Now what if I wanted to take vector A and take it from square root of 20 down to a length of 1? Then I just take that vector A, which I could write in a couple different forms. I'm going to do in this column vector form. How could I take 20 and multiply it by some value, let's call it m, and make it turn into 1? What would m have to equal? Oops. 1 over root 20. So we take the vector and we multiply it by 1 over the magnitude of the vector. And that gives us the unit vector. That's what that little hat on top of that A means. It's the unit vector. Likewise, for vector B, we get 1 over root 13 times the direction vector given. Oh, that was a really good bracket. Let me do that again. Go back. Oh, disappeared on me. Now, when I want to find the angle between those 2 vectors, I'm going to call it theta. There's a couple things I could do. I could find the length between these 2 and use law of cosines. That's one way you could do it, but then you'd have to do the distance formula and then use law of cosines. That's a lot of work. I don't really want to do that. So to find the angle, we know that the cosine of the angle between the 2 vectors is A dot product B, or A dot B, as I like to say, over the magnitude of one times the magnitude of the other. All right, so let's see if we remember the dot product. I had -4, so A dotted with B. A was -4, -2. B was 3, -2. I take my x components and I add them to the product of my y components. And it looks like I get -8. Look good. -12 plus 4 is -8. So the cosine of the angle in between is going to be -8 over the product of the magnitudes, which is square root 20, square root 13. So just looking at this ratio right here, since this value is negative, I'm already anticipating that this angle will be obtuse because a negative cosine puts us in quadrant 2. Would you please plug into your calculator the following and find the value for theta? Would you confirm that you get what I get? All right, so this slide here is the introduction to line to vector conversion. Okay. What I like to think of this as, this looks very similar to something that we're used to seeing. Kind of looks like this. Right, are you with me? Very similar to the equation of a line. And I want to kind of draw a parallel of what's going on here. What is B? B is like our y-intercept. It's a point that we know on a line. In this vector equation for a line form, that's what A is. It's like the point that we know the vector originates from. Okay. Okay, what does M represent in this equation? Slope. It's kind of like our direction vector B. Okay, so if a vector takes on, let's say our vector B takes, I don't know, 2, -3. Well, that's really just a slope, because what does 2 represent? It's the change in what? Our change in x, right? It's our horizontal movement. So to the right 2, what is this? Change in y means down 3. So what would our slope be for this vector? Yeah, that's just our change in y over change in x. That's all it is. It's hidden in this vector form. Okay, so let's say that, for example, a vector, let's call it r, starts at a point, I don't know, 7, 3, and then goes a certain number of steps. I think of this as like steps, right? And your steps could be positive, so they could end up going in a certain direction, or negative, which would flip the direction of your vector. And it travels at some direction vector. I call this the direction vector. And so there we go. We know a point and we know a slope. So check this out. This is a really cool conversion. If I know a point and I know a slope, couldn't I write the equation of a line using those two things? Yeah, I use this form. This is called point-slope form, where I just fill in my values. And that's now in Cartesian form. It's just now an equation of a line. All right, so there's this nice connection between vectors and lines, and I'm going to teach you a little bit more about that in a moment here. Okay, so what I call A is like this initial point, right? And then I call B this direction vector. It's your direction vector. So when I refer to direction vector, that's what I mean. Okay, let's continue. That means go forward. There we go. Come on, forward. Here's the proof of that. I'm not going to go over that. You can spend your time on that. Here are the 3 forms. Now, they might look confusing here for a moment, but what I said before was I had R equals A plus lambda B, right? But A and B are vectors themselves. They're written in column vector form, so they have components x, y, and z. Typically, we're just going to stick with x and y. I could take that from vector form to parametric form. Very easy conversion. Look at this. Where does this show up? Parametric form. Pretty straightforward, right? If I just distribute lambda to each of those values, A, B, and C, they show up over here. So then y would equal y1 plus lambda b. And then likewise for z. Okay, we'll get to Cartesian form in a moment. Okay, but that's how we draw the connection between vectors and Cartesian form in a moment here. Whoa, that's the end of the lesson? Kind of. I want to go over a couple of the problems even in the homework. Okay, so let's make a vector equation in vector form, parametric form, and Cartesian form if we know, right, this is our point, and this is our direction vector. Well, vector form should be pretty easy then, right? I could write it in this form. R equals the point plus lambda times the direction. Yeah. Sweet. Okay, now, it might be smart for you to start thinking that R is just a location, just a point. So I can get to any other point going from a point using a slope. Yeah. So I think of it as xy instead of r. And that makes the parametric form that much easier. Let's talk through it. What would x equal? 5 plus what? 5 lambda, yeah? What would y equal? Negative 6 minus 3 lambda. Cool. Okay, so now how do I go from one to the next? Well, you could do what I did on the last slide, which was find the slope and use the point, or you could go through this Cartesian form. So when I get to Cartesian form, which of these three variables is no longer? Lambda, correct. So I want to basically eliminate lambda. I'm going to do that here. See how we can do. So if I want to eliminate lambda, let's solve for lambda. So I would take x, I would subtract 5, and then what would I divide by? 5. How about in this one? What would lambda equal? Y plus 6 divided by negative 3. Okay, so if they're both equal to lambda, they have to be equal to each other. So y plus 6 divided by negative 3 would be equal to x minus 5 over 5. Well, now let's just solve for y. Okay, first of all, let's know this. Cartesian form, that's done. Finished. Hiya! Finished. I don't need to go further. But if you want to come up with the Cartesian equation just isolating y, well, I'd multiply both sides by negative 3. And notice how I split the terms. Okay, and then from there, I'm going to subtract 6. And what would that be? That's 3, that's 6, that'd be minus 3. That'd be the equation of the line that would represent that vector. Yes, sir? Oh, folks at home, you just missed something real good. Shouldn't have paused it. Okay, so in this one, what's different? I got 2 points, so I don't have a direction vector. Oh, yeah, you do. Yeah, you do. Okay, I got x, y, right? That's r. Which point do you want to start at? 3, 9? Oh, thanks for that. That's going to make my brain explode, but that's cool. Okay, so we're going to start there. Well, how do I get to the other one? How do I go from 3 to negative 2? I subtract 5. And how do I go from 9 to 7? I subtract 2. Oh, so there's the vector form of that. Right? So it's just a slope. That's all it is. It's just a change in y and a change in x. All right. Oh, this is so easy. This is going to take me 0.1 minutes, which would be what, 6 seconds? Oh, shoot, I got to go fast. Are you ready? What do I want to do? Find the vector equation of line. Hey, x, y, where does it go? It goes through 2, 5. How does it get from that point to the next? It goes right 3 and down 4. That was like 9 seconds. Woo! There's a point. There's a direction. Oh, cool. All right, find a vector equation of a line passing through the points A and B. Oh, no. Well, I know that any point on the line can be represented by starting at a point. Thanks, Chloe, for giving me a difficult one last time. I'm going to use a different variable. It's going to be scary. This is called mu. This is the cow's favorite Greek letter. Mu. Yeah. There's the vector equation. Why doesn't it make sense? Yeah, plus 2. Jean. Plus 5. How? All right, this one's going to take me less than 0.5 minutes. I know that. Don't judge, okay? Ready? I'm going to fill in a few blanks. Here we go. Here's some blanks. Here's some blanks. Let's do these blanks first. I see how many x's? I see an x. I see a 9. I see a 1 lambda. Yeah. Oh, then I see a y. Then I see a 5. Then I see a -3. I can do that. That's a vector equation for that parametric representation. Okay. Oh, this is scary. Find the parametric form. Oh, gosh. Well, isn't R just xy? Yeah. So wouldn't x be -8 plus 2 mu? Y equals 10 plus. I'm done. That's the parametric representation. Oh, are you scared of number C? Yeah, you're scared of number C, aren't you? Yeah, you are. You're scared.
Why do we switch from lambda and mu?
Because we wanted to, Hari.
That was given.
It's just a variable. Oh, x, y. Oh my gosh, I'm scared. No, I'm not. I'm not scared at all. X, y equals, oh no, what did I want? Parametric? Yeah. Oh, then that means x equals 5 plus mu over 2. Divide by 2. And y equals 3 plus divide by 2. Oh, I forgot a 5 here. That's cool. That's 5 over 2. All right, this is setting foundation for your upcoming lessons. So we got 2 more lessons. We're going to find out where vectors may collide or intersect or maybe even possibly miss each other in the night. Yeah. And then bowling balls, they're going to collide. And you can win stuff like a general store $1.50 gift card. I know, that'll get you like a piece of yarn and a candle. Okay. Maybe one of those miniature ones. Yeah, like a little one. Have a nice day.